Ever wish you had a crystal ball? A way to see the future? Well, in chemistry, we kind of do. And today, we're going to learn exactly how to use it. So picture this. You mix some chemicals, a reaction kicks off, but what's the end game? Where does it actually stop? Does it run all the way to completion? Does it fizzle out halfway, or does it barely even start? And believe me, this is way more than just a textbook question. The answer to this determines if a new medicine will actually work or if an industrial process is even profitable. The stakes, yeah, they're incredibly high. Okay, so before we can predict the future, we need to learn the language of the reaction. So first up, we're going to decode chemical change and figure out how to track it as it happens. Let's dive in with a classic from our source material, ammonia breaking down into nitrogen and hydrogen. Now, the most important things on this slide are those numbers out front, the coefficients. They are the secret code that tells us how everything changes together. So here's the key idea. If the amount of nitrogen goes up by some amount, let's just call it X, then everything else has to change in a fixed ratio. It's like a recipe, right? For every 1 scoop of nitrogen you create, you have to create 3 scoops of hydrogen, and you must use up 2 scoops of ammonia. It's this perfectly synchronized dance of molecules. All right, I get it. Tracking all those X's can get messy and fast. But don't worry, chemists have this brilliantly simple tool for keeping it all straight. Let's talk about the ICE table strategy. It's called an ICE table, and it's basically just a super simple grid that helps us organize everything we know about a reaction's journey from its start to its final destination, equilibrium. And the best part? The name tells you exactly what to do. ICE. I stands for initial, what you're starting with. C is for change. That's where our buddy X comes in. And E is for equilibrium. You just add the first 2 rows together. Simple, right? And this is what it looks like in the wild. Just 3 simple rows: initial, change, equilibrium, and a column for every chemical in the mix. Trust me, this little grid is about to become our best friend for solving some seriously tough problems. Okay, we've got the language, we've got our map. Now it's time for the main event. Let's put it all together. We're going to take these tools and solve a real chemistry problem. All right, here's our mission. We're starting with 1.00 m of PCl5, and we're given this special number, Kc, which is the equilibrium constant. Our job? Figure out the exact concentration of everything once this reaction finally settles down. First things first, we build our ICE table. For the initial row, it's easy. We have 1.00 of our reactant, and, well, we haven't made anything yet, so the products are 0 and 0. For the change row, the reactant goes down by X, and each product pops up by X. It's all very logical. Now, here's where that special number, Kc, comes into play. The formula for Kc is always the products divided by the reactants. So we literally just grab the values from our equilibrium row, which would be X and X on top and 1.00 minus X on the bottom, and set the whole thing equal to that Kc value we were given. So we do a little bit of algebra, we crunch the numbers, and boom, we solve for X. This one little number is the key. It is the single piece of information we needed to unlock this whole puzzle. And this is where the magic really happens. We take that value of X we just found, we plug it back into the equilibrium row of our table, and just like that, we have our final answers. We've done it. We've used our chemist's crystal ball and predicted the future. Okay, so the math is cool, I get it, but what does it all really mean? For our last section, let's zoom out. Let's talk about the deeper meaning of equilibrium and what it tells us about the entire universe. You see, that K value isn't just a number for a calculation. It's telling us a story about the reaction's personality. If K is big, like greater than 1, it means the reaction is an overachiever. It loves making products. But if K is tiny, the reaction is kinda lazy. It's perfectly happy just staying put as reactants. But why? What's the real driving force? Well, it all comes down to a concept called free energy, or delta G. Think of it like a ball on a hill. A negative delta G means the reaction is rolling downhill. It'll happen all by itself. A positive delta G means you'd have to push it uphill. And at equilibrium, that's the bottom of the valley. The system is stable. It's found its balance. And here is the absolute kicker. These 2 big ideas, free energy and our K value, are just 2 sides of the same coin. A reaction that wants to roll downhill on its own, well, that's going to have a big K value. A reaction that needs a push to get going, that'll have a tiny K. It's all connected. So here's the ultimate takeaway. Every single reaction, whether it's happening in a beaker, on a lab bench, or inside a distant star, is trying to do one thing: get to its point of minimal free energy. And that destination? That's what we call equilibrium. It's pretty wild when you think about it, isn't it? We started with a simple table for organizing numbers, and we ended up talking about the fundamental driving force of the entire universe. It just makes you wonder, what if that ultimate tendency of everything to find its most stable state is all hidden right there inside that single number, K?